Okay, good morning all of you. So let us continue with our topic, that is real numbers. Today we are going to deal with the next aspect of this topic, that is fundamental theorem of the arithmetic. So our next, that is fundamental theorem, that is fundamental theorem of arithmetic. That is our next topic. So first of all, let us write down the statement of the fundamental theorem of the arithmetic. According to this theorem, every composite number every composite number can be expressed as a product of as a product of prime as a product of prime, and this factorization is unique, and this factorization is unique except for the order except for the order in which they occurs except for the order in which they occurs means every composite number can be expressed into its prime factors, and this factorization is unique except for the order in which they occurs. For example, let us take a very simple example. If we want to express any number, for example, 6. Now 6 can be written as 2 into 3. Means we have expressed 6 is a composite number. We have expressed 6 as a into its prime factors, 2 into 3. And this factorization is unique except for the order. We can write as 3 into 2 also. Now let us solve few questions that are based on the fundamental theorem of the arithmetic. So let us take the one question first. Okay. Now explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers are composite numbers. Okay, we have to explain why these two numbers are composite numbers. Okay, since we are aware of the fact every composite number can be expressed into its prime factors. Okay, or composite number means any number having more than two factors is a composite number. So let us come to the solution of this question. First we solve the first question. The first number is 7 into 11 into 13 plus 13. Now if we take 13 as the common, because 13 is the common factor in these two numbers, so we can take 13 as a common factor. The remaining numbers 7 into 11 plus 1. So 13 into, that is 78. Okay, so we have expressed this number as a two factors. Now this number is more than two factors, 13, 78 and 1 is the factor of each and every number. So that's why this number is a composite number. Similarly, for second part we can solve like this. Second part is, that is 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. Again 5 is the common factor, so we can take 5 as the common. Now remaining number is 7 into 6 into 4 into 3 into 2 into 1 plus 1. Okay, now again this number is the multiplication of two numbers. That's why again this number is a composite number. So okay, by this way we can prove the uniqueness of the fundamental theorem of the arithmetic. Now let us solve one more question. That is our next question, that is second question. Prove that there is no natural number Prove that there is no natural number. Prove that there is no natural number for which for which 4 is to power n ends with the digit 0. Okay, what we have to prove, there is no any natural number for which 4 is to power n ends with 0. So let us come to the solution of this question. Okay, any positive integer ending with the digit 0 is divisible by 5 and its prime factors must contain the pair of 2 into 5 for unit digit to be 0. Okay, so if we write down the prime factor of this number, 4 raised to power can be written as 2 into 2 whole power n. Now, since this number contains only a pair of 2, but there is no any pair of 5, so that we can form a digit 0. That's why now there is no any such value of natural number is possible for which this number ends with the digit 0. Okay, so here we can write, since there is no any pair of since there is no any pair of 2 into 5, okay, this number so that this number never ends so that this number never ends with digit 0, so that this number never ends with digit 0, because there should be at least one pair of 2 into 5 for unit digit to be 0, but the prime factorization of this number is of the form 2 into 2. There is no any single pair of 2 into 5. Now let us write down the few more important results. Now we come to our next topic, that is some important results. So our next topic is, that is some important results. Some important results. In this topic we will discuss about the few important results which are used very frequently. Now let us come to the first important result. Here we can write p is a prime number. Here we can write let p be a prime number. Let p be a prime number. Let p be a prime number and a be a positive integer and small a be a positive integer. Be a positive integer if, okay, then we can write if p divides a square, if p divides a square, then p also divides a, then p also divides p, then p also divides a. Okay, that is the first result. Now let us come to the proof of this result. How can you prove this result? Okay, so we come to the proof of this. Uh, for the proof of this number, we use the fundamental theorem of the arithmetic. So we can write from the fundamental theorem of arithmetic, 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 a can be factorized as the product of primes, as the a can be factorized as the product of primes, as the product of primes. Okay, so we can write like this. Let us write down a can be expressed into its prime factors. So a is equals to p1, p2, then p3, and so on up to pn. Okay, here we can write where p1, p2, all these numbers are prime, and p1, p2, p3, and so on up to pn, not necessarily distinct, not necessarily distinct. Okay, means these prime factors can be repeated also. Now we can write, if we square this equation both sides, if we want to find the value of a square, then by squaring both sides, then a square can be written as, that is p1 square, that is multiply by p2 square, then p3 square, and up to so on. Finally pn square. Now it is given that p is a prime and it divides a. Okay, now we can write, now it is given that, now it is given that p is a prime, that it is given that p is a prime and it divides, and it divides a square. Therefore, okay, it divides a square. Therefore p is a prime factor of a square. P is a prime factor of, p is a prime factor of a square. So from the uniqueness part of the fundamental theorem, okay, so next we can write, from the uniqueness part of the, from the uniqueness part of fundamental theorem of arithmetic, of fundamental theorem of arithmetic, from uniqueness part of fundamental theorem of arithmetic, fundamental theorem of arithmetic, it follows that, it follows that only prime factors of a square, it follows that only prime factors, only prime factors of a square are, only prime factors of a square are p1, p2, and so on up to pn. Therefore, therefore p is one of, therefore p is one of p1, p2 up to so on pn. That's why we can say, since only prime factors of a square are p1, p2, pn, therefore p is one of p1, p2 and p3. So we can say that p also divides a. That is the first part of the fundamental theorem of the arithmetic. Here we can write one more result. That is, let us write down the second important result. That was the first result. Now we can write down the second result. Let x be a rational number. Let x be a, let x be a rational number. Let x be a rational number whose decimal expansion terminates, whose decimal expansion, whose decimal expansion terminates, whose decimal expansion terminates. Then x can be expressed in the form p by q. Then x can be expressed, then x can be expressed in the form, then x can be expressed in the form p by q, where p and q are co-primes, where p and q are co-prime, where p and q are the co-primes, and prime factorization of q, and prime factorization of q, and prime factorization of q, prime factorization of q is of the form, is of the form 2 to the power m into 5s to power n, is of the form 2 to the power m into 5s to power n, where m and n are non-positive integers, where m comma n are non non-negative integers. where m comma n are non-negative integers. Okay, so what we have written here, if a decimal expansion of this number terminates, that means prime factorization of the number q must be of the form 2 into 5. Then only the decimal expansion of this number terminates. Otherwise, the decimal expansion of this number does not terminate. Now, let us see, let us solve few questions that are based on this result. That is our first question. Uh, Here we can write, without actual forming the long division, we have to state which of the following is terminating decimal expansion. Which of the following is terminating, which of the following is terminating decimal expansion. Okay, without using the long division method. The first one is 13 upon 3125. Second one is 14 upon 35. Okay, now let us check. Here we can say, in the first question, we come to the solution of the first question. In the first question, that is 13 upon 3125, if we look at the prime factorization of the denominator, that is of the form 2 to the power 0 into 5 is to power 5, means the prime factorization of the denominator is in the form of 2 into 5. That means the decimal expansion of this number is terminating. Okay, so here we can say it is terminating. We can write it is terminating decimal. It is terminating decimal. Now if we check the second number, if you want to check the second number, that is 14 upon 35. Okay, here we can write 14 upon the prime factorization of this number in the form of 7 into 5. Okay, so if we check this number, 7, 14 get cancelled out 2 times, that is 2 upon 5. Okay, so if we look at this number, again the factors of the denominator is in the form of 2 into 5. So again this number has terminating decimal. So again this number has terminating. So such type of questions, without using the actual division process, we can state that whether the number have terminating decimal expansion or not. We can state directly by just looking at the prime factors of the denominator. Okay, that's for today. Then we will continue in the next lecture.